It'll be a quick story, not longer than 8 minutes, actually shorter than that. One thing that I really enjoy about all of AI is how simple it is relative to how impactful it is. Unlike something like quantum mechanics or some other complicated physics or complicated chemistry or math, AI is really simple. You just have those artificial neurons, which are inspired by biological neurons. And there is a math formula consisting of 3 equations that tells you how these neural networks should learn. It's called backpropagation. And it's the kind of thing which you can explain to a high schooler that knows math in about half an hour. But the magic is that the result has been so impactful. And so what ended up happening is that there is one recipe, essentially one recipe, that's been powering every single thing that's ever been done that's also cool in AI. The recipe is you take a big neural network, a big digital brain running on a big computer cluster that's running this learning formula, which I described to you, that I told you about but did not describe, and you just feed it a lot of data. And then what you'll see next is how we vary this formula, how we change the neural network, how we change the data, and the downright magic that ensures. You know, when I started OpenAI with our co-founders more than 6 years ago, I was motivated by a belief that neural networks will continue to surprise us and to make the kind of incredible progress that they've made. And it's quite likely that the progress that neural networks are making, the progress that they have been making, will keep going on for quite a while. I don't think anyone here believes that neural networks will slow down. And so their impact will be very vast. They will touch every aspect of society, every part of human activity. And so with this belief, we thought to create OpenAI to not only fulfill the original sci-fi promise of AI, to realize it, but to also make it benefit humanity with all that entails. But now I want to go and dive into some of the technical details and tell you about some of the neural networks that we've built. Because time is so short, I will go quite quickly through them. So GPT-3 is just a really big neural network whose training objective is to guess the next word. Well, you could say, what's so special about guessing the next word? The thing about guessing the next word is that it's something you can do in math. You can just measure how good your neural network is at guessing the next word. But if you do a good enough job at that, if you guess the next word well enough, you must understand something. And the better you guess the next word, the better you understand. Imagine a mystery novel where the detective is about to unravel the identity of the criminal at the end of the book. If you paid attention, you might narrow down the appropriate next word down to 2 guesses, maybe even to 1 guess if you paid really close attention. So now you have a link between guessing the next word and understanding. So GPT-3, I think many people are familiar with it. At the time, it was quite surprising and unprecedented that you could just communicate with a neural network in this way, ask it questions, ask it to do stuff, do few-shot learning. It was a big surprise. Now it's been almost a year and a half ago, more. Old news. We're not surprised anymore. Tough crowd to please. One cool thing I want to mention are the use cases of GPT-3. One of the cool things about these models is that they're no longer science projects. They're useful. So GPT-3 has been exposed through the OpenAI API, and it's been used in production by hundreds of companies. I'll mention my single favorite use case called the Trevor Project, where they use GPT-3 to pretend to be disturbed teenagers to train therapists to talk with real disturbed teenagers. So I think that's my single favorite application of GPT-3. I think it's legitimately quite cool, if I may say so myself. I'll briefly mention GitHub Copilot. It is a collaboration we've done with Microsoft, where we trained a really good neural network to guess the next word in code. Unsurprisingly, a neural network can do that task quite well also. GitHub Copilot is really popular. Programmers love it. And the users of GitHub Copilot, like 30% of the code that they commit is written by Copilot. So that's a pretty good statistic. And of course, as with all these neural networks, this is not the end point. This is more of an appetizer. Things will get a lot better. You may also have heard that we have made some progress on image generation with DALL-E. You know what it can do. You give it text, it produces an image. Why do it? We've made a lot of progress in text-only models, but the world is not just text. And I don't think anyone here believes that the powerful AIs of the future will be text-only. I'll just show you some cool images that I like. There's many more on the internet, but on the text, you have the caption that produced the particular image. I like this one. I mean, really, those are pretty good images. This one is, I think, caught the attention of many. I think Percy had this one in his slide as well. I like this corgi in the shape of a fish. It's pretty good compositionality, I have to say. You have to understand fish and corgi and the way it would look like if they were to be combined. Fur monster in a purple room. I think it's a very appropriate fur monster. That's quite a beautiful photo of this family of mice with like the zoom in, like the blurry background. Very artistic. Just a beautiful painting. I think that's quite meta. So I only have 1 minute, but I want to tell you about safety and deployment. You know, as I mentioned, our goal at OpenAI to not only build general AI, not only realize the promise of sci-fi, of the AI sci-fi of old, but also make it beneficial. And what that means is that we will be what it means is that we are building increasingly more powerful AI systems. We make them safe and we figure out how to deploy them. And I'll describe to you the high-level process that we use for deploying these systems in the remaining 30 seconds. And we've done quite a bit of work on this process with DALL-E. And in short, it consists of 3 steps, the high level. We do a lot of planning ahead of time, where we try to think about the many ways in which it could go wrong, the kind of biases that it may have, the kind of misuse potential that we really don't like. We make decisions. How do you trade off the exciting, cool applications with the negative applications? What kind of restrictions do you want to put on it? We do training, where we modify the training data and do additional training after the fact to modify the capability of the system. So for example, with DALL-E, we modified it so that it is unable to generate recognizable faces. It took us additional work to remove this capability. And then, of course, when we deploy our model, we put it on our servers behind an API. And we gradually increase the surface area of its application. And we carefully fine-tune the usage restrictions as we learn the ways in which people use those models and misuse them.
So I have 2 questions, one very short for anyone, probably Ilya. How much does it cost, everything, training, salaries of the researchers, you name it, to produce one of these foundational models, to know how high the barrier is? So that would be the first question. The second is for Rob. I want to challenge, so I agree with that there is a problem, no question, but I want to challenge the FDA as the perfect model. ProPublica has made a great reporting about each of the large big pharma companies has been fined for malicious marketing of drugs. It's a legalized drug cartel. Do we want to create another one of those?
Okay. So Ilya and then Mark.
Thank you.
Yeah. So I can't comment on the precise cost of these models, but it is indeed the case that they're not cheap to make. And it's not just the compute. You also need to have a really strong team working together for quite a while. So yeah, I mean, my expectation is that for if, let's say, universities want to participate in the creation of these models, they need to do what Stanford has done, which is to basically band together and organize a lot of resources. And in particular, I think that one place where universities need to build some muscle is on the engineering side. Because you can get money, you can get compute. Mm-hmm. But then the natural way in which universities do research is different from the kind of organized effort that's needed to really push such a system. So I think that this would be another organizational hurdle that universities would need to overcome to participate.
But it's in the range of, say, tens of millions of dollars, hundreds of millions of dollars. It makes a difference, the range.
I understand, but unfortunately I can't comment right now.
Yeah, I think there are some papers you can read on that, but let's turn to Rob.
I don't mean to point to the FDA or the idea that we should create an independent federal agency, the Digital Technology Agency or something. I meant that as an analog. Here's what biomedical research has built out over the course of decades, and here's what is absent from AI science. I don't think we port the professional norms and institutional design from one domain over to another domain. So I mean it as a way to think about the density of the institutional design. And of course, we need to come up with purpose-built answers for the age of AI.
Okay.
I have a question for Ilya, but for anyone in the panel. Given all the advancements in multimodal, multitask foundation models, how do you define AGI? What are the milestones to get there? And is embodiment key for it? Or what are the other requirements people aren't talking about?
How to define AGI? So it is indeed the case that AGI is a little bit of an ambiguous term. It's not used very precisely by people who use it. It should be understood as more of an aspirational goal, kind of like a North Star. And the way you can tell that we have reached the age of AGI is when you have lots of computer systems. Like one way to tell, here's one way to tell, is when most of the economic activity is done by some kind of an AI. This is an objective criterion. Because if someone comes to you in the lab and says, oh, check out what I got, how can you really know whether you're being shown something real or not? But if you are living in a world where the economy is growing really fast because AI is doing the great majority of all economically valuable work, that's how you know that AGI has been reached. I mean, I think that the current models are really exciting. They're making a lot of progress. And like the way to really measure their impact is like how much are they being used to in the real world to actually solve problems. Like I would say that right now, these models are just breaking out from the lab. Until very recently, AI would make a lot of exciting progress on benchmarks in the labs. It would be really cool science projects, just starting to get out, starting to impact the real world. So there's still lots of work that needs to be done. The models need to get so much better, so much more reliable, need to explain ourselves, really collaborate with us in order to solve problems. All these things need to happen. We are seeing very small steps in that direction. Things will be a lot more exciting in terms of how much these systems can do.
Okay, let's take a question from Feifei, and then you'll be after that, Pat.
Yeah, okay, I'll start with the intriguing technical question, possibly mostly for Ilya, but interested from the technologists too, is that when we look at that corgi fish picture from DALL-E, frankly, for average human, it's very hard for an average human to draw a corgi fish. In the meantime, for average human, it's very easy if I ask you to draw a toy cube tower that would fall under gravity. Like that concept of a simple tower, toy tower fall. So there's a discrepancy. I think that's going to be hard for DALL-E. So there's a discrepancy between what's easy for human to generate and what's hard for machines. Do you want to comment on what in the making of these transformer models that create this discrepancy between, DALL-E and humans?
Yeah, I can comment on that. So I'd say, so that question, there are actually two different sub-questions. In the case of DALL-E in particular, it was designed, there were certain engineering and design choices that were made, which are not inherent. They were made for convenience in order to make the system have certain better properties. So Because of that, it is not as good at some of these tasks which you mentioned, but those limitations can be lifted. I do want to point to a deeper, more fundamental difference between these neural networks and human beings. These neural networks, they have more breadth and less depth. Like if you consider a language model may have read far more books than a human being ever would. But a human being understands the information that they've consumed more deeply. So I think that this is the more fundamental discrepancy between human beings and AI. So it is indeed the case that there are many more scientific breakthroughs that can be made to improve those systems. Despite this discrepancy, there are still clear avenues for improving those systems, and so they will still get a lot better. And perhaps over time, those discrepancies will diminish as well.
I think I would agree that basically the next step is really using video because you have all the motion information. I mean, basically Feifei's example for tubes falling, you need motion information to learn from them. You have all the corresponding information with audio and speech, so you have a much richer corpus of information, right? And I think you can also see obviously the video as an extension from the images, right? It's not because you can generate an image from text. The next step would be you could generate a video from a sentence, right? So I think it's not either or, but I would say video allows you to do much more. And then I guess video has the multimodal information. And one thing of these foundation models or these transformer models that they can really capture this multimodal information very well, right? It's much easier to design multimodal representations with these models because they can learn automatically what corresponds between the different modalities. And then obviously, if you want to go towards more general intelligence, you need to also interact with the world. But that's something I think we don't, we just start to see how these models can actually integrate interaction with the environment. And so I think that would be the next step.
Okay. Do you have a comment, Ilya?
Yeah, just a brief comment is that one way we can think about the progression of these models is that of gradual progress. We've made a lot of progress in text-only models, and we were surprised by what they can learn. We have added another modality, perhaps not perfectly. Perhaps this is not the final way in which we will add the modality. Some exploration will need to be done. But eventually, I think it is a reasonably safe bet that we will figure it out as well to find a very useful packaging of the modalities so that the system will know more, understand the human world better, and be able to interact with us better because of them. So it's a technical problem that will likely be solved.
Okay, great. Right up the back, yes.
My name is Evelyn. I was a Stanford student, and I took my first AI class with Professor Liang. So I really appreciate it, Professor Liang. And you mentioned the process of adapting a general model to a specific domain. So I guess my question is actually to Ilya. I have built an application using GPT-3. And by the way, OpenAI has a very good safety review process. I went through the process, got the approval, and rolled out a global launch. What I observe is that the option to customize the general model to a specific domain is very limited. Although there are options, but it's very limited. So my question is, what is OpenAI's plan to allow more customization and configurability of the GPT-3 or DALL-Es?
Yeah. You should expect that that the ability to customize these models will increase in the future, customize them through fine-tuning. I do want to make, however, so I should say, it will become easier and the tools to do so will become more powerful. But I also want to make one other comment, and that's about the likely shape of customizability of these models in the future. One point of view, which I happen to believe in right now, is that if you take a model, any neural network, and you have some kind of benchmark, and you fine-tune the neural network on this benchmark, you'll get really good performance on the test set. But that doesn't actually mean that your system is that good. And that's something we've seen a lot also. I think it was most apparent in the kind of intermediate years, maybe like the mid-2010s on ImageNet, on the ImageNet dataset, where people started to report human-level performance on ImageNet. Yet the systems were obviously not human-level not at the human level. So what does that mean? Like, I think what that means is that there is hidden overfitting going on when you fine-tune. And so I think that several things will need to happen. Like, the fine-tuning technology itself will need to improve so that you'll be able to preserve a lot of the generalization of these powerful base models. And we'll actually find that zero-shot evals give you the best and most reliable, like, representative performance. What you can get zero-shot or few-shot, you know that's on your test set, you know that's the performance you're going to get in the wild. So it's a much more honest measure of performance measure for yourself as you evaluate your system.